Examples of random processes. In this, already the first episode has been seen. The second random process which we have taken for study is the semi-random binary transmission process. Okay, let us now go into the details of this process. Let us now go into the details of this process. Right, we are talking about semi-random binary transmission process. The word binary tells you it is 2. The problem of transmission of random binary information across a channel is basic one in communication theory. So this is a basic one in communication theory. A source generates a sequence of two symbols, say H and T. Compare this with tossing a unbiased coin where H represents the head and T represents the tail. Then, since the coin is unbiased, the probability of getting a head P of H is equal to the probability of getting a tail P of T, equal to half for a single trial. The sample space now consists of a doubly infinite sequences of heads and tails. This S is equal to the set of all eta, where eta equal to q minus 1, q naught, q1, q2, etc., where qi belongs to the closed interval h, t. With the above sample space, probability measure, and Borel field equal to the power set, the semi-random binary process x of t using 1 and minus 1 as values is described on each sub-interval of time axis as follows. It is given by x of t, eta equal to 1 for h equal to q of t and minus 1 where t is equal to q of t. This process is ensemble of time waveforms that change from 1 to minus 1 or remain the same at possible transition time points that are equally spread at a distance t apart along the time axis. Right. Now, having known this function, what function did we learn? X of t comma eta. What is this? This is your process, the semi-random binary process x of t. Having now understood that x of t comma eta is 1 when q of t is h and minus 1 when q of t equal to t, we move further to study the characteristics of this particular function. Right. When we start with the characteristics, let us first find the first order density. So first order density first order density. By considering the process at an arbitrary time t, a random variable is defined. Since the values of x of t for all t are either 1 or minus 1 as seen before, this is possible. Also, during each interval, the random variables are all the same. It is discrete. It is discrete for each t. It is discrete for each t in the time interval capital T. This is very obvious because we compared this with tossing a coin, which is once again a discrete event. Okay, so this time interval t is now going to range from it. This interval t we are going to take from I into t to the next consecutive interval I plus 1 to t. The probability of getting a head, we have seen already, probability of getting a head or the probability of getting a tail equal to half because it is unbiased. So the first order density is so the first order density is given by your fxt of xt value equal to, I will have half into delta of xt plus 1 plus half into delta of xt minus 1. This is the first order density and this is for all t. This is for all t. Next, we move on to find the mean of this process. So, the mean is given by E of x of t. You would have noticed even in the previous lecture for the straight line process, we use the same notation, eta x of t. Now this value is nothing but integral minus infinity to infinity. I will have xt f xt of xt into dxt. So this when expanded will give me integral minus infinity to infinity. I am going to substitute for fxt from this equation. So I will have integral minus infinity to infinity xt into half delta xt plus 1 plus half delta xt minus 1, the whole thing into dxt. So this value, one value is 1 and the other value is minus 1, and this gives us half into minus 1 plus half into 1, and this value gives 0. Hence mean equal to 0. Next, let us find the second order density. Right. In order to find the second order density, let us consider x1 and x2 to represent. X1 is nothing but x of t1 and my x2 as x of t2 for arbitrary times t1 and t2. Please remember, they are discrete random variables which take the values plus 1 and minus 1. This we should always keep in mind. Therefore, their joint density function, therefore, their joint density function is given by f of x1 comma x2 equal to p of x1 equal to 1, x2 equal to 1 into delta of, I will have x1 minus 1 comma x2 minus 1 plus, I have to consider all the possibilities. I will have probability of again x1 equal to 1 and x2 equal to minus 1 into delta of x1 minus 1 comma x2 plus 1 plus, I will have probability of x1 taking minus 1 value, x2 taking the value 1 into delta of, I will have x1 plus 1 comma x2 minus 1. Then both taking negative values, so x1 equal to minus 1 and x2 also equal to minus 1 into delta of, I will have x1 plus 1 comma x2 plus 1. So all these four are possibilities. Now if t1 and t2 are different, so if t1 and t2 are different, x1 and x2 are independent variables. Obviously x1 and x2 are independent. Why are they independent random variable? I am denoting by capital RV. Why are they independent random variable? Because the tosses were independent. As the tosses were independent, we have probability of x1 equal to t, comma x2 equal to t will be equal to probability of x1 equal to t. Here this value is 1 into probability of x2 equal to 1. So this probability we know is half. So half into half, value equal to 1 by 4. Similarly, let us consider x1 is minus 1 and x2 is 1. Probability of x1 equal to minus 1 and x2 equal to 1. Again you can split this to be probability of x1 equal to minus 1 into probability of x2 equal to 1. So this again will land up for us as 1 by 4. So in all these cases, whatever we consider, that is both are 1s, minus 1 1, or I can even take this as plus 1 minus 1, or if I take this as probability of x1 equal to again both negative minus 1 comma minus 1. Instead of writing it individually, I thought we will just give it together. Okay, so we will just write it together instead of repeating the steps again and again. The value simply becomes 1 by 4. So this is nothing but probability of x1 equal to, I have both positive, negative, positive, positive, negative, and this is equal to x1 equal to minus 1 comma x2 equal to minus 1, x1 equal to minus 1 and both negative, x2 equal to minus 1. In all these cases you will be finding that the value ends up to be 1 by 4. Therefore my joint density function f of x1 comma x2 is now nothing but, I will just be having 1 by 4 taken common outside into delta of, I will have x1 minus 1 comma x2 minus 1 plus delta of, I will have x1 minus 1 comma x2 plus 1 plus delta of x1 plus 1 x2 minus 1 plus delta of x1 plus 1 comma x2 plus 1. So this would be my joint density function for t1 t2 in different intervals. Suppose they are in the same interval. Next, for if t1 and t2 are in the same interval, they are in the same interval, then what happens? If they are in the different interval, we saw previous case, suppose they are in the same interval, then the probabilities are obtained using conditional probability because they are in the same interval. So what happens? I will have probability of x1 equal to 1 comma I will have x2 equal to 1. This is nothing but probability of a intersection b is the same as b intersection a. So I rewrite this as x2 equal to 1 restricted to x1 equal to 1 into my probability of x1 equal to 1. That is, P of A intersection B is P of A restricted to B into P of B. This formula we are using. So in the same interval, in the same interval, what happens? Probability of x2 equal to 1 given x1 equal to 1, this probability is 1. Therefore, I will have probability of x1 equal to 1, comma x2 equal to 1 will be 1 into half, because probability of x1 equal to 1, that we have to consider, that may be half. So 1 into half, value equal to half. Similarly, probability of x1 is minus 1 and x2 equal to minus 1, that probability will also be 1 into half, the value equal to half. For all other cases, the value will be 0. That is, probability of x1 minus 1 and x2 equal to 1 equal to probability of x1 equal to 1, comma x2 equal to minus 1. In both these two cases, it is 0. Therefore, what happens to our joint density function? My joint density function fx1 x2 of x1 comma x2, this value now becomes half into, I will have delta of x1 minus 1 comma x2 minus 1 plus delta of, I will have x1 plus 1 comma x2 plus 1. Okay, so this will give me delta of, I will have x1 plus 1 comma x2 plus 1. This would be the joint density function, or in other words, this is our second order density. Next, having found the second order density, we will next go forward to find the autocorrelation function. Okay, so how do I deal with this autocorrelation function? Again, I will consider two cases. T1 and T2 are in the same interval, T1 and T2 are in different intervals. So first let me take T1 and T2 are in the same interval, same time interval. Okay, then what happens? I have to write autocorrelation Rx of T1 comma T2. This is nothing but expectation of, I will have x of T1 into x of T2. So this, in other words, by the notation I mentioned above, x of T1 is x1, x of T2 is x2. So this is equal to integral minus infinity to infinity. It is double integral. So again minus infinity to infinity x1 x2 f x1 x2 of x1 comma x2 dx1 dx2, provided the joint density function is known. Okay, as f of x1 comma x2 is different based on the cases of our t1 and t2, either lying in the same interval or in the different interval. Now let us deeply analyze this expression. Okay, so I told you they are lying in the same interval. So when they are lying in the same interval, let me rewrite the autocorrelation function. This would be minus infinity to infinity, minus infinity to infinity. I will have x1 x2 into half delta of x1 minus 1 comma x2 minus 1 plus half delta of x1 plus 1 comma x2 plus 1. Okay, for this I need to integrate with respect to x1 and I also need to integrate with respect to x2. This value, however, is half into 1 into 1 plus The probability here is minus 1 into minus 1 into half. Total value will become 1. So Rxx of t1 comma t2 is two dimensional. It is a two dimensional snake of block functions. So it's a two dimensional snake of block functions. So we will be having a straight line to represent our axis like this. Okay, so with this straight line we will be having block functions. Say you have a block here, and again you will have another block somewhere over here, and you may have one block in the baseline too. So let me consider this. So this is how that function would look for us. There would be a block in the baseline too. Then from here to here we would be having a connectivity running. From here to here we may have a connectivity running. From here again the block runs, and from here again the block runs here. So this is how the block would go. So this would be my t1, and on top this vertical axis would be my rxx of t1 comma t2. Okay, so this is two dimensional snake of block function. Therefore my rxx of t1 comma t2 is a two dimensional snake of block function along the line t1 equal to t2. Right, suppose they are in different intervals, then what happens? That is our idea. Suppose they are in different intervals, then what happens? So now for t1 and t2 in different intervals, if t1 and t2 are in the different intervals, then what happens? I have to redo my rxx of t1 comma t2, and this value is now going to be equal to, I will have integral minus infinity to infinity, I will have minus infinity to infinity x1 x2, I will have a 1 by 4 constant throughout into delta of, I will have x1 minus 1 comma x2 minus 1 plus delta of x1 minus 1 x2 plus 1 plus delta of x1 plus 1 x2 plus 1 plus delta of, I will have x1 plus 1 comma x2 minus 1, all this into dx1 to dx2. So this would give me the value as 1 by 4 into 1 into 1, isn't it? x1 minus 1 x2 minus 1, so 1 into 1 plus, I will have a 1 into minus 1 plus, I will have minus 1 into minus 1 plus, again I will have a minus 1 into 1, and ultimately when I see it is 1 plus minus 1 plus 1 plus minus 1 giving me the value to be 0. So we should be very careful when calculating our autocorrelation function to check whether t1 and t2 lie in the same time interval or in the different time interval. Finally, we are going to discuss the stationarity of this process. Right. So it is stationary in the mean. Why is it stationary in the mean? Because we have mean value to be equal to 0. Therefore, it is a constant and hence it is stationary in the mean. Okay. So, and stationary of order 1, and it is stationary of order 1. Okay. The first order densities are not a function of time. Because it is equal to 0, so it is independent of time. Therefore, we claim that it is stationary. However, the semi-random process, however, the semi-random process is not stationary of order 2, is not stationary of order 2 and above, of order 2 and above, because the second order densities are not the same. You see, as we take whether t1 t2 are going to lie within the same interval, value 0. When different interval, value is coming. Therefore, what happens? There are shifted versions of time differencing by a set amount. Therefore, it is not stationary in autocorrelation. Therefore, it is not stationary in autocorrelation. Therefore, what can I conclude? Therefore, it is not a WSS. What is this? Wide sense stationary process. It is not a wide sense stationary process. This is our ultimate conclusion. So, in this video, we have discussed about stationarity. We have seen how the autocorrelation function behaves for t1 t2 in the same interval and in different interval. We have also evaluated the mean, we have evaluated the first order density and the second order density of semi random binary transmission process, which is one of the most common in communication study. Thank you for your attention.